Hello everyone, in this video we'll take our first look at the 65816 and start hooking it up on the breadboard. We'll also look at the bank address latching circuit from the datasheet. Hope you enjoy! So let's start hooking things up. So I have here a brand new breadboard. This is a busboard BB830, should be a pretty good quality breadboard. Now I always turn my breadboards around so that the power connections are shorter for most of the chips. I have here 65C816. Okay, so I'm gonna add power. And then power LED. So this LED is actually interesting. It's LED with a built-in resistor. So I can plug it in directly on the power rail without adding a separate resistor. Let's try it on. Okay, looks like it's working. I'm also gonna add a couple of decoupling caps. So I have a pretty big 220 microfarads directly where the power is coming into the project. And for each power rail, I'm going to add 10 microfarads. Also need to bridge the power. I'm actually going to do this on the left. Okay. There you go with power. Okay, so if you look at the datasheet for the 65C816, you can see that most of the address pins are here, and then they wrap around to the other side of the chip here. But there's only a small amount of them here. So it would be nice to bring them all in a line down here so that hooking up the other breadboard is going to be easier. So let's do that. So this is going to be A12, A13, A14, and A15. Now we can actually do the same thing with the control inputs that are on the top of the chips here. Let's bring them down here so that we have everything in a line. So that's going to be the reset, VDA, the MX status pin, the clock, Phi2. This is bus enable. This is the emulation status pin. Finally, the read-write signal. Okay, let's also add power. Power is pin 8. And then ground is over here at the top. And the decoupling cap and the power input. Okay, so this should be all the pins that we need here on the bottom. Now, the data pins at the top here are actually multiplexed. So let's take a look at the data sheets in order to understand how the data pin multiplexing works. So I have here the data sheet from Western Design Center of the 65816. As you can see, the CPU can address 24 bits of address space. So that's 16 megabytes of memory. And if you look at the pinout, you see there's only 16 address pins exposed. So when they designed the 65C816 as a replacement to the 6502, they wanted to keep the same form factor. And so the 6502 is a 40-pin package. And so they didn't have enough space to put all the address pins that they wanted. So they decided to multiplex them into the data pins. So what does that mean? Well, if you look at the data/bank address bus, which are pin D0 to D7, the datasheet says that the data bank address bus pins provide both the bank address and data. The bank address is present during the first half of a memory cycle, and the data value is read or written during the second half of the memory cycle. There's some timing diagrams in the datasheet that we can look at, but they're not really clear. There's a lot of things happening. They mixed a lot of info into this diagram, and there's some stuff missing, so I redraw the diagram. Okay, this is a simplified diagram that shows clock running at 14 megahertz, so that's a 70 nanosecond period. So each cycle is 35 nanoseconds. And the state of the D0 to D7 pins in a read cycle or in a write cycle. So as you can see, the data is read by the CPU on the falling edge of the clock, and then on the rising end of the clock, the pins output the bank address. And in a write cycle, you can see that the CPU outputs data on the falling edge of the clock, and then on the rising edge of the clock, it also outputs the bank address. So we have to build a decode circuit to be able to latch the bank address when the clock is rising, and keep a memory of it during the whole cycle, so that the read and the write can target the right space in memory. So there's actually a circuit for doing that in the datasheet. You can see that the bank address is latched using a 573 or a 373 latch chips. The data for the latch chip comes from the data pins, and we latch the data on the falling edge of the signal, which is the inverted clock. So that's the rising edge. So this is where the latch chip would latch the data. If you look at the datasheet for the 74AC573, which is the chip that we're going to be using, you can see a description of how the chip works. The 8 latches are transparent latches. So when the latch-enable input is high, the outputs follow the inputs, which means that any change at the input is immediately reflected at the output. And when the latch-enable signal is taken low, the outputs are latched at the logic level set up at the inputs, so that it memorizes what was present at the inputs when the latch-enable signal went low. How is it going to look like in the circuit? Well, first we have to consider the actual circuit that we're going to be building. I just created a new project in KiCad here, and I'm just going to quickly transcribe the circuit that we already built on the breadboard. Okay, so that's what we built in the breadboard. So we have the power input with the big decoupling capacitor, the power LED with a 220 ohms resistor, which for mine is built in. Then we have a decoupling capacitor per power rail, and then finally a decoupling capacitor per chip. And we have connected some of these input pins to the bottom of the breadboard. Okay, so if we want to build the decoding circuit, we need an inverter to the clock. I'm going to use a 74HCT04, and that's going to take the clock as an input. And it's going to output the inverted clock. So how does this inverted clock signal look on the timing diagram? I've made some updates to the timing diagram. First of all, this is now based on a 10 MHz clock, just to give us some breathing room, because 14 MHz is crazy fast, and we can talk about what it takes to run at this speed in a future video. The period is now 100 nanoseconds, so each cycle is 50 nanoseconds. The CPU read and write timings are updated to match. So we now have bit bigger bank address interval and a bit bigger data write interval. So let's look at the timing of the 74HCT04, which is the inverter I'm trying to use. We can see here, looking at the switching characteristics, at 5 volts, the maximum propagation time, so that's TPD over here, which is the time it takes for an input to be propagated to the output, is specified as a maximum of 25 nanoseconds. Well, actually between 23 and 25. Let's use 25. And the datasheet doesn't actually give us a minimum. It does say, though, that the typical value is 14. So I'm going to assume 10 as a minimum. It seems like a reasonable value. Let's see what it looks like in a timing diagram. So this is the clock signal inverted through the 74HCT04. As you can see, it has a 10 nanosecond minimum propagation delay, which means that the earliest point where we could see a change value is 10 nanoseconds after the clock pulse, and a maximum propagation delay of 25 nanoseconds, which means that the latest point we could see a value change is 25 nanoseconds after the clock pulse. So there's a zone here that is undefined, and this means that the change would happen at any time during these points. And that's the same thing for the writing edge of the clock. The same delays apply. We can already see that it's going to be a bit tricky, because the latest point where we could see a change in the latch-enable signal is over here, where the bank address has already disappeared from the multiplex pins. And in fact, if we look at the datasheet for the 75573, we can see this in the timing requirements at 5 volts. We can see that we need the data to be set up before the latch enable goes low at the minimum of 3.5 nanoseconds. And we need the data to be held after the latch enable goes low for 2 nanoseconds. And in fact, if we show the setup and hold time requirements on the timing diagram, we can see that we might be able to match the setup time, because at this point the bank address is still valid, even if our estimation of 10 nanoseconds is a bit off. We see that we have some margin here, but for the hold time, we're definitely not in the interval. And so that's because the CPU actually stops outputting the bank address 10 nanoseconds after the clock went high. So we have to find a faster chip. We need this transition to happen much earlier so that the hold time requirement is satisfied. So let's look at another chip. We can take a look at the 74AC04, which should be faster. I have here the datasheet for the 74AC04. And if we look at the switching characteristics, we can see that it has a maximum of 7.5 nanoseconds propagation time and a minimum of 1 nanoseconds. And so these values are much lower than the HCT version, and we might be able to make it work. So let's see how it looks on the timing diagram. So this is a signal inverted with the HCT version, and this is the signal inverted with the AC version. As you can see, the hold time for the data is now met. We have maximum 7.5 nanoseconds after the clock pulse, plus 2 nanoseconds here, that's 9.5. So we are below the 10 nanoseconds where the bank address starts changing. And the setup time is also met because we have quite some margin before the clock pulse to latch the bank address. All right, so this should work. Let's add the 573 to our circuit and plug it in on the breadboard. KiCad doesn't seem to have the AC version I'm using, but that's fine, we can change it later. There we go. So that's the data and bus address pins connected to the 573. Now we want the load signal to come from the inverted clock. And output enable, we're going to tie it to ground because we want the chip to always be enabled. This is everything connected, so I'm just going to update the chip so that it shows the correct version I'm using. Excellent. So let's build a circuit on the breadboard. So if you look at the datasheet for the 573, you can see that it's actually wired in the other way around that we want, meaning the inputs are at the bottom and the outputs at the top. And we have the data pins that we need to decode at the top here. So I'm going to have to plug this the other way around. Let's add power now so we don't forget that the chip is flipped. VCC is actually going to be here, and ground is going to be at the top here. Then we have an output enable line, and we want that to be tied low because we want the chip to always output its content. And then we need the data pins. So let's transfer them over here. So this is D0. Okay, so now the output pins are going to be here. That's going to be the bank address. And it's going to be in the right order. So the least significant bit is here at the left, and the most significant bit is here at the far end of the latch chip. The last pin that we have to hook up in the latch chip is the latch-enable. And so we need an inverter. So I have here 74HCT04 hex inverter, and we're going to use it to invert the clock. So just reordering some wires here. So I can get the clock from here. So this is our clock line. We're going to invert. We need power to this chip here and here. And we also need decoupling caps here and here. Okay, so this is the latch-enable. And that's it. So our latch chip is completely wired up. And so now we're going to have the bank address available on the pins here. Just need to tie the unused inputs of the inverter high, because it's a CMOS chip. If we go back to the datasheet for the 74AC573, we can look at the propagation delay in the switching characteristics. And so this table is a bit more complicated. The way I think about it is, if you want to know how the data travels through the latch, you have to look at the propagation delay from the input to the output. And the second line here gives you the propagation time between the latch becoming transparent and the value at the output starting to change. We can see that input to output is a maximum of 11.5 nanoseconds with a minimum of 2. And when the latch is opened, the outputs start to change between 2 and 11 nanoseconds later. So this is what it looks like. You can see here, beginning of the clock cycle, when the latch is opening. We know that this happens between 1 and 7.5 nanoseconds after the clock pulse. This is our second line in the datasheet here, when the latch is opening. The timing for that are 2 to 11 nanoseconds. And so in order to draw the timing, we have to add the minimum to the minimum and add the maximum to the maximum. So we know what's the best and the worst case that can happen. Between here and here, we know that it's undefined. After that, we know that the latch is transparent. So it's actually passing through what's present on the CPU pins. And we know that at this point during the diagram, this is undefined, which is why I put here undefined pass-through. Then once the CPU pins have a stabilized bank address, we want to know when this is actually available in the transparent latch. For that, we have to look back at the first line from input to output, and we know that's 2 to 11.5 nanoseconds. So from the time that the CPU has the bank address on the pins, we know that it could be at best 2 nanoseconds and at worst 11.5 before the bank address is available on the latch pins. And then after that, the latching happens, but this has no impact on the bank address because it's already present here before the latching. As you can see, the latching chip actually memorizes the bank address for a good part of the second part of the clock cycle, up until 3 nanoseconds after the falling edge of the clock. Depending on how we build our address decoding logic, this might be a problem here. We know that the CPU has data hold time of 10 nanoseconds, which means we need to show the CPU the data that we wanted to read for at least 10 nanoseconds after the falling edge of the clock. But if the address starts to change here, we might start outputting the wrong data here. So we'll have to keep a look at that. I'm going to ignore this problem for the moment, and we can go back to it in a future video once to build the address decoding logic. All right, so there you have it. This is the first part of the bank address latching circuit. And in the next video, we'll continue implementing the latching circuit from the datasheet, and we'll take a look at how the actual data pins buffering work. Hope you've enjoyed it. Let me know in the comments if you have any feedback, and I hope to see you in the next one. Goodbye.